All right, please let's look up. We'll be looking at the derivation of Michaelis Menten's equation. So we'll be deriving from the scratch Michaelis Menten's equation. And one thing about it is not long. It may look long, but it is not long. So just follow from the beginning. And anywhere you don't understand, please ask questions. Now, don't write until we are done. I'll give you time to write. Now, if you want to derive Michaelis Menten's equation, all you have to do is to consider an enzyme and substrate binding to the enzyme. So, if you look at this, we use E to represent enzyme, right? Then, if substrate binds to the enzyme, you agree that we have enzyme substrate complex, right? And catalysis can take place and product will be given off, right? But we know that enzyme is not used up at the end of the reaction. So at the end of the reaction, we still have our free enzyme. Now, if you are deriving Michaelis Menten's equation, this is the first step. So to derive Michaelis Menten's equation, start with your free enzyme plus substrate. So if you add substrate to it, we have enzyme substrate complex. Catalysis will now take place. Enzyme will be formed. Enzyme will be gotten back. Then our product is formed. Now, one thing you need to note here is this. This arrow here, is it forward reaction or backward reaction? This one at the top. Forward, right? Now, the kinetic constant for this forward reaction is given as K1. For this second one, is given as K2. Then this one, is it forward reaction or reverse reaction? Reverse reaction, right? So, what will be the kinetic constant? No, K minus 1. It's still for the first reaction, but we're using minus to show that it is a reverse. Is it not? Now, this is our first step. The next thing you have to do is to consider all these kinetic constants. But before then, we have two assumptions in Michaelis Menten's equation. And the two assumptions now let's look at this. If we have something like this, if you are plotting a graph of concentrations against time, you notice that if you have candle and you light it, candle is the substrate, right? As you light the candle, what will be happening to the concentration of the candle or the length of the candle? Will it be increasing or reducing? Reducing, right? So it will be reducing. So if you notice, concentration of substrate was high here, but with time it will be reducing, right? It will be going down. So this concentration of substrate. Then the product of burning that candle is what? Wax, right? What will be happening to the concentration of the wax? It will be increasing, right? As the candle length is decreasing, the wax is increasing, the product is increasing. So product will always be increasing. Concentration of product will always be increasing. But you agree with me that if substrate binds to enzyme, we have enzyme substrate complex, right? Now, at the beginning of the reaction, the concentration of enzyme substrate complex will be increasing until it becomes steady. That increase in substrate concentration will no longer increase the enzyme substrate complex. Now, this is enzyme substrate complex at a steady state. One assumption of Michaelis Menten's is assuming that the rate of formation, the rate of the reaction here of ES, enzyme substrate complex, is constant. Because as you can see here, it's just steady. So that's why they call it steady state kinetics. Now, they assume that the S over the T is equal to 0. The S over the T is rate, right? Rate of change of substrate of enzyme substrate complex. I told you earlier on that when they say rate, it's talking about relative to time. So the rate of change of enzyme substrate complex is equal to 0. Please just listen to the end. as usual. After I finish, we'll clean the board, we'll take it again. Now, this is the first assumption, that the rate of change of enzyme substrate complex is equal to 0. Now, the second assumption of Michaelis-Menten's is that the rate of formation of enzyme substrate complex is equal to the rate of breakdown of enzyme substrate complex. That the rate at which enzyme substrate complex is formed is equal to the rate at which it is broken down. For it to be steady, for it to be stable, it means the rate at which the candle is decreasing is equal to the rate at which the wax is forming, right? Now, the second assumption of Michaelis-Menten's equation says that the rate of formation, please, I'll use this to represent rate of formation, or let me use arrow F. So the rate of formation of ES is equal to the rate of formation, or the rate of what? Breakdown of ES. Please, in exam or anywhere, write it out, rate of formation. I'm using arrow F and arrow B2. So rate of formation of ES is equal to rate of breakdown of ES. Now, let's come back to this first equation. If we want to write kinetic constant K1, K1 will be equal to what? Remember, kinetic constant is always concentration of product over concentration of what? Reactant, right? Concentration of product over concentration of reactant. So we'll be having concentration of the product here is this, right? ES all over concentration of the reactant. Is it not? But I said when you're writing it, you don't put this plus. So concentration of E times concentration of S. If you notice, if we want to make ES the subject of the formula, we cross multiply, right? So we'll be having ES to be equal to what? K1 ES, right? This stuff we have here, this stuff, this ES to be equal to K1 ES is the rate of formation of ES. This is the rate of formation of ES. Now, the second thing we'll consider, what if we want to consider the rate of breakdown of ES? What we want to consider the rate of breakdown of ES? What will be the rate of breakdown of, if the rate of formation of ES is kinetic constant times this, what will be the rate of breakdown of ES? The rate of breakdown of ES will be equal to, now if this is breaking down, you know it's going back this way, right? So if I'm breaking this down, it's just like ES, I'm breaking it down to E plus S, is it not? So if I'm breaking it down, this becomes our product, right? So the rate of breakdown of ES will be what? Concentration of what? Concentration of E, concentration of S all over what? All over ES, right? And you know this is the same thing as this is the kinetic constant, there is what? K minus 1. So this will be K minus 1. So if I make ES the subject of the formula, it means I'll be having ES to be equal to what? K minus 1 ES, right? But on the second thought, if you check this, the rate of breakdown of ES can be broken down to give you this, and ES can also break down to release free enzyme and products. Listen, ES can be broken down to release E and S, and can also go the forward direction. So ES can be broken down also to give enzyme and products. So if I'm to write the kinetic constant here, K2, how will I express it? K2 is what? Concentration of product all over concentration of reactant, right? This is a forward reaction. So I'll be having concentration of this all over what? ES. Now, as usual, if I'm to make this the subject of the formula, I'll just cross multiply, right? So I'll be having K2 ES. Now, I would like you to listen up here. The rate of formation, we've gotten the rate of formation, right? Remember the second assumption. The second assumption was that the rate of formation is equal to the rate of what? Breakdown. And from that second assumption, the rate of formation was seen as what? This was the rate of formation, right? K1 ES. This was the rate of formation. So I can say K1 ES is equal to the rate of breakdown. The rate of breakdown was seen as what? Note now, this one is if the ES is broken down to the reverse direction, and this one if it is broken down to the forward direction. So the rate of breakdown will be this plus this. Do you get? The rate of breakdown will be this one when it is reverse plus this one when it is forward. So rate of breakdown will be K minus 1 ES plus K2 ES. So what I did here was from the second assumption that says the rate of formation of ES is equal to the rate of breakdown. And we've seen that this is the rate of formation and this is the rate of breakdown. The next thing we are going to do is this E here. This E here represents free enzyme. Represents free enzyme. Now look at this. If you have something like this and you have if we have 4 enzymes, let's assume that the enzymes have one binding site and you have 2 substrates here. You agree with me that this substrate will bind to this other enzyme, right? This one will bind to this other enzyme, right? Good. If we want to calculate the number of free enzymes present, what do we do? How do we calculate the number of free enzymes present? No, we don't know the free enzyme. We want to calculate the free enzyme. Total enzyme minus what? Enzyme that is bound, right? The total enzyme present, you know the total enzyme is 1, 2, 3, 4. 4 minus enzyme that is bound is 2. You have 2, right? 2 free enzymes. So free enzyme is equal to total enzyme minus what? Enzyme substrate complex. Enzyme that is bound. Now, the next thing you have to consider is, as you see this E here, you have to replace this free enzyme with this one we've gotten now. Because we've seen that free enzyme is equal to total enzyme minus enzyme substrate complex. So, K1 into, instead of E now, you write the whole of this, right? So you now write concentration of E total minus ES. Remember that this one here represents only the E, right? We still have S outside. Equal to, I write the whole of this back. K minus 1 ES plus K2 ES. Now please just follow me. The next thing after this is, I can open this bracket, is it not? If I open this bracket, remember there are 2 things outside the bracket. So if you are opening the bracket, you take note of the 2 things outside the bracket. So K times this will give me what? K1 ET. S will still multiply this one. S. Then minus this one times this one give me K1 ES S. So I just open the bracket, taking note of the 2 things outside the bracket. Now this is equal to, I'll say write this one back. K minus 1 ES plus K2 ES. We're almost done. Just like I said, it will look long, but if you follow the procedures, it's just straightforward. Now, the next thing we have to do is, I will cross over this one. I will rearrange the equation by taking this one to the right hand side and leave this one here. So I'll just take this one to this other side. So here I'll be left with K1 E total equal to, if I'm taking this one to this side, it becomes what? Plus, right? Because it was minus here. So I'll be having K1 ES S plus K minus 1 ES plus K2 ES. Yes. The S is also multiplying the one inside the bracket. ES. K1 times ES is K1 ES. S times CS. Not what? No. If the S was alone, this is ES, not just S. If the S was alone, that is when it will be S squared. Good. Now, if you look at this side, what is common with everything here? Yes. ES is common here, right? So I'll factorize out ES in that on that side. So here I'll be having K1 E total S equal to, I'll bring out ES. Now if I bring ES outside the bracket, what will I be having here? K1S plus, what will I be having here? K minus 1 plus what? K2. Now, the next thing you have to do from here is divide throughout by K1. The next step now, we said divide throughout by what? K1. So you divide through by K1. Can I clean this side? Can I clean this side? Please write this side so I can clean that side. All right, so we are going to divide this equation through by what? K1, right? So I'll take this whole one, this one on my left. The one on my left, I have K1, E total S. We are dividing through by what? K1, right? So this is over K1 equal to ES. Please, I would like you to listen up here. This one, I can do KI S all over K1, sorry, plus K minus 1 plus K2 all over K1. Now look at this. If I decide to do if I decide to do one of them all over K1, it's still the same thing. Like I can break this down to K minus 1 all over K1 plus K2 all over K1. But we have a reason why we are doing it like this, and you will see it now. But before then, you agree with me that K1 we cancel K1, right? This K1 here we cancel this K1 here. So we are left with E total substrate concentration equal to ES into, here we are having S plus K minus 1 plus K2 all over K1. Now, it is a known fact that K minus 1 plus K2 all over K1 is equal to Michaelis Menten's constant. It's equal to Km. K minus 1 plus K2 all over K1 is equal to Michaelis Menten's constant. So anywhere we see the whole of this, I'll just put what? Km. So the whole of this gives us Michaelis Menten's constant. So we'll be having ET S equal to ES into S plus what now? Plus Km. Because everything here is equal to Km. Now, the last step you have to take now is we have to divide through. We have to make ES the subject of the formula. And if we are making ES the subject of the formula, we'll divide through by what? By this, right? To make ES the subject of the formula, this ES, we have to divide through by this. So I'll be having ES equal to what? I'll be having ES equal to ET S all over what? S plus Kn. We're almost there. Did I say the last step before? Now, the last step now. What you have to do is multiply through by K2, and that's the last step. Then you get your Michaelis-Menten's equation. So, multiply through by K2. So, if you multiply through by K2, here we'll be having K2 ES equal to K2 ET S all over S plus Kn. You know, if you are multiplying through by K2, it's just the upside that the K2 will be. Can I clean just part of this? Alright, so now we've divided through, we've multiplied through by E2. The next thing is, just look up. E2 ES. This is equal to initial velocity. This is initial velocity. Then K2 E total is equal to maximum velocity. When we started with an equation. We started with E plus S to give us ES and what? E plus P, right? And we call here K1, here K2, and here K minus 1. Now, if we're looking for K2, we said K2 will be this over this, right? If K2, we said, please don't write this part. K2 is concentration of products all over concentration of reactants, right? So if we make this the subject of the formula, we'll be having K2 ES. So this part here, where enzyme substrate complex is converted to product, is the initial velocity. As you can see, this part is from this part, is the initial velocity. Then if the total enzyme is involved, then that's the maximum velocity. So basically, anywhere you see K2ES, you put what? V0, initial velocity. Anywhere you see K2ET, you put Vmax. So from this equation, K2ES, I will not be writing this again, but I'll write what? V0. So V0 is equal to K2ET. This is now what? Vmax, right? So Vmax times S all over S plus Km. Or you say Km plus X. Me, I like writing Km before X. Any of them you write, they are correct. But I like writing Km before X so that the X will align. This equation we have on the board is called the what? Michaelis-Menten's equation. This is the Michaelis-Menten's equation. V0 equal to Vmax substrate concentration all over Km plus S. Now, if you plot this on graph, you will not have a straight line graph. What you'll be having will be something like this. And if you are plotting, this is, let's say this is velocity, then here, what will I be plotting here? Substrate concentration. Now, this point, the velocity of the reaction, as the substrate concentration is increasing, the rate of the reaction will be increasing until to get to a point when the enzyme active site is saturated. So the reaction proceeds at a steady rate. At a steady rate. This point where we have the highest peak or plateau is called what? Vmax, maximum velocity. Is the maximum velocity. Now, the maximum velocity, if you trace down the maximum velocity, if you have something like this Vmax, half of Vmax will be somewhere here, right? Now, half Vmax. If I trace this point down, this becomes Km. Km is the substrate concentration at half Vmax. Km is the substrate concentration at half Vmax. But the problem here is, since this is not a straight line graph, most times they will ask you to plot Michaelis-Menten's graph. What they ask you to plot is Lion-Weaver-Burg, because Lion-Weaver-Burg converted this to a straight line graph. Eddie Hofty converted it to a straight line graph. Hans Wolff converted it to a straight line graph. Alright, so write this.